right, let's get started. All right, so I want to remind you that the final exam is a week from Thursday. So that's Thursday, December 12th, 10 days from now. It's for the regular section, section 1, it's 3:30 to 5:30, either in here or next door, depending on your last name. And for the hybrid section, it is from 6 to 8. If you're in the hybrid section and you can't make that time, but you can make the regular section, go ahead, and vice versa. Bring your U card, and you can bring 2 sheets of notes, one more than last time. Question?
So that means that'd be 4 pages because that's 2 front and back?
Yeah, 4 sides of 2 sheets. Yeah.
Cool.
Okay. Any other questions? In the lab tomorrow, the T's will go over an old exam. I think the one from last year. I'm not sure which one I gave them. And then in lecture, we'll do a review in lecture on Wednesday. Okay. In the meantime, you've got the final assignment, the asteroids assignment, due on Thursday or Friday. And don't forget your sort of end of week report. Looked like a lot of people forgot their end of week report last time, so I opened it up. It's still open, I think, as of now, until the end of the day, if you forgot to submit after 5 points. And there'll be a similar one at the end of this week. Any questions about that? Is that going okay? Yeah?
Is the end of week report GS 11C?
Say again?
Is the end of week report GS 11C?
I can't remember the letter. I bet it's D. Anything else? Okay. We were talking about sorting last time. I wanted to talk a little bit more about that. You remember this is a scatter plot. It shows the elements of an array. In this case, the size of the array we're looking at is 256 elements. I can make it smaller. There are 16 elements. So you can think of this axis, remember, think of this as indexes into the array, so 0 through 15. And each element of the array is shown up here, and the higher the element, the higher its value. So down here at the bottom left is the number 0, and then 1, and then 2, and then 3, all the way to 15. So that's what it looks like when it's sorted, and this is what it looks like when it's put into descending order, and this is what it looks like when it's permuted, scrambled up. And we've been looking at we looked at a couple of sorting algorithms last time to sort of whet your appetite for 2420. Let's remember what they were. I'm going to go back to, say, 128 here. We'll permute. And we're going to sort. I'm going to put the speed at moderate, and we're going to sort using selection sort. Right? So you remember the way selection sort works is it scans through the array, finds the smallest element, swaps it into the first spot in the array, and then repeats that, ignoring the first spot in the array, finds the next smallest element, swaps out into the second spot in the array, and so on. So it gradually builds up from left to right. And at any given point, if we pause, then the left portion of the array is perfectly sorted, and the right portion is still yet to be incorporated into it. So we will start again from there. So that was selection sort. Then this was insertion sort. It's a little bit different. If I pause in the middle of it, what you see is the left portion of the array is ordered, and it's in ascending order, but it's not that straight line yet because there's some elements yet to be put into that ordering. And what happens is each pass through the array, we You take the next element that we encounter, moving from left to right, and basically push it down to the spot it belongs into. So right now, you see that red box is it's getting close to where it needs to be. So you'll see the elements sort of slide down till they get where they belong. Some of them slide a long way down, some just slide a little bit of the way down. And gradually it gets more and more like a straight line until we hit the end. Okay, when you study algorithms, you end up doing some counting, trying to predict the behavior of the algorithm without having to run it. And I told you last time that both selection sort and insertion sort are quadratic algorithms. What that means for our purposes is that for a quadratic algorithm, if you double the size of the input, you quadruple the running time. So I showed you that last time. If I put the speed up at fast here again, this is 128 elements. So if I permute it, and our stand-in for time is going to be the number of comparisons that are performed because that dominates the time for the algorithm to run. So we'll do insertion sort on size 128. And it did a little under 4,000 comparisons. If I permute it again, well, that's the wrong thing. If I double it in size and then permute it, instead of a little under 4,000, it's going to do, well, it varies depending on how it's randomized, but it did around 16,000, so about quadrupled. If we repeat the experiment with selection sort, we'll start with a big array. You notice it's already going way past insertion sort. About twice as many comparisons as insertion sort on average. So it took 32,000, so I'll take about 8,000 to do the half-size array. Okay? So algorithm analysis is something that you'll start learning how to do if you take 2420. And with algorithm analysis, you think about the description of the algorithm or look at its code or whatever, and you're able to say, this is a quadratic algorithm. And then you know something important. You know what's going to happen to the algorithm as the size of the input grows. That's something that we care about a lot. All right, so that's all stuff we talked about last time. Any questions I could answer about it? Yeah.
So just give me 1 moment. There were some on the practice test. It said there were different kinds of algorithms. We're going to go over those today.
Particularly which ones?
I'm just trying to find them.
Quick sort, merge sort, maybe?
Yes, those two.
Yeah, we're going to talk about those too.
Thank you.
Okay, now, yeah.
Do you have any good mnemonic devices for remembering the algorithms?
Okay, so he's asking for a device to remember the names of the algorithms. Insertion sort, I don't know if you've ever played bridge or any card game where you got to pick up a bunch of cards and sort them in some fashion. The way some people do it is they pick up the first one, and then they pick up the second one and move it to where it needs to be, and the third one and move it to where it needs to be and insert it, and the fourth one and insert it at the right spot. So that's one way to remember insertion sort in terms of inserting cards into a hand. Selection sort, I guess each pass you're selecting the smallest element and then putting it in the right spot. But that may not be helpful. Any other questions? All right, let me show you something else here. I'm going to go to comparison control. And what we're seeing here let me permute this again, is we're doing selection sort. So a selection sort, remember, makes a pass, finds the smallest element, swaps it into the first column. goes through the rest of the elements, finds the smallest, swaps it into the second column, and so on. And so as it does that, as it moves across, it's doing comparisons. So what this box at the bottom shows is the first line in the box at the bottom is going to show us every comparison, every spot that was compared to in the first pass. Then the next line down will show us every comparison that was performed in the second pass, and so on. So I'll just run it. So we have a picture of the comparisons performed down here, and there's the final sorted array. So why does it look like this for a selection sort? Why is every single box in the first row down here? So this first row of little boxes, why is it black all the way across? Yeah?
Because it has to compare to everything to make sure it's the smallest.
Right. We have to look at every element and compare every element to find the smallest one. Now, why is the second row not quite as long as this? Okay?
Because it's doing the exact same thing except you have to go to one less.
Right. It's no longer looking at the first element of the array, it's just looking at the rest of the elements. So every pass, every time there's an outer loop that's doing this, the number of comparisons required for each pass gets smaller and smaller. What do you notice about the area of the square that is colored black? Yeah?
It covers about half of it.
It covers about half. So what is the size of, what's the area of an n by n square? N squared. And the number of comparisons to sort an array of size n, the selection sort, is about 1/2 n squared. That's where the quadratic comes from. It's the number of comparisons is proportional to the square of the length of the array. Now, if I did the same thing for insertion sort, where am I doing? Insertion sort, and permute it. What do you think the picture of the comparisons look like down here? First of all, about what proportion of the box do you think would be shaded in? Yeah? Quarter. Because we know insertion sort on average is about twice as fast as selection sort. Okay? But what will it look like? Each row will correspond to taking an element and pushing it down to where it belongs. So will it be as uniform as selection sort?
No. Except a straight line will be curved.
We don't know that it'll be curved, but it's not that there's not an equal amount of, well, it won't be a regular geometric feature. It's easier to see it and then explain what you're looking at. So let me start this. So first of all, could you believe that's about 1/4 n squared shaded in? A quarter of the square shaded in.
Yeah.
I mean, clearly half of it's white. And what's left? Yeah, I can imagine half of that is white and half is black. So what does it mean? Look at this one right here. This line, this black line starts all the way over to the left and is solid all the way to the right. What happened with that element when we sorted that element?
Had to go through everything before we found it.
Yeah, that particular element wanted to go to the beginning of the array. And so it had to be compared to everything to its left in the array at that point. On the other hand, there's some really short lines, like this white line right here. We had to do only a few comparisons during that part of the of the run. Why is that? Yeah?
It was near the top.
Right, it wanted to be near the top of the existing array, so it only had to be pushed a few spots to the left. So on average, each of those black lines is about half the distance from the diagonal to the side. Some of them are long, some of them are short. On average, you fill about half the space. But that's on average. What do you think happens if we run insertion sort on an array that's already sorted? Yeah?
You just get one line that goes without like one diagonal.
Right, we get one diagonal. It's like I got a little bug, there's a little discontinuity up there. Why does it look like that? It seems like every element only had to be compared once, and then it was exactly where it wanted to be. It didn't have to be repeatedly compared and moved till it percolated where it needed to be. Why is that? Okay?
Because everything already was where it wanted to be.
everything was already where it needed to be. And so it just took one comparison to confirm that it didn't need to move, and then we're done. So another thing you learn about algorithms is sometimes you look at the average case behavior. Sometimes you look at the best case and the worst case. So in the best case, insertion sort runs in what we call linear time. The number of comparisons is proportional to the size of the array. Now, what would happen if we doubled the size of the array, but left it ordered? Would we expect the number of comparisons to quadruple like before? Okay, so but it did 4,400 there. So if I come up here and change the size to 256 and sort, well, okay, we got 255 here. I don't know what I was looking at before. Let's try again. 127. So you get about half the comparisons when it's half as big. So that's linear, a linear time algorithm. What do you think would be the worst case for insertion sort? Okay.
It's in descending order.
If it's in descending order, we get the worst case. So let's put it in descending order and run the algorithm. And you'll see it takes about twice as long as it did in the average case. Every element, each time we encounter an element, we have to push it all the way to the beginning of the array because it's completely out of order. What about selection sort? Do you think selection sort would have dramatic differences between best and worst case? Yeah, it turns out it doesn't. So if let's put it in ascending order and do the sort. It takes no advantage whatsoever of the fact that it's already sorted. It does just as much work that way or this way. The animation looks different, but, or this way. So those are just some things, without delving into the exact code of the algorithm, things you can observe just by watching it. The quadratic behavior of both algorithms and the dramatic difference in the best and worst cases in the case of insertion sort. But both of them are, in the average case, quadratic algorithms. Let's look at a different one. We're going to look at merge sort. So I'm going to run it. Let me run it and you tell me if you can tell from watching how it's working. Okay? That's a trick question because it's just too hard to see what's happening. So let's permute it. Let's put the speed down to moderate. A little easier to see what's happening. Yeah?
It's splitting in half, merging the two sides, then putting them together, then doing it again.
Okay. Did you tell that from watching, or did you already know that?
I kind of
Okay. So the way merge sort works is it splits the array in half. It recursively, using merge sort, it recursively sorts the first half. It recursively sorts the second half. Then it has two. In fact, let me try to stop it when it's done sorting the two halves. So here we are. Let me start. So it's still working on the first half. Got it sorted. Now it's working on the second half. And I stopped it maybe a little bit too soon. But anyway, it made one recursive call and sorted the left half of the array. It made another recursive call and sorted the right half of the array. Now, how can it combine those two halves to obtain an overall sorted array? How can it take advantage of the fact that both sides are now sorted? Yeah.
Is that like another recursive call?
It's not another recursive call, it's a loop. Okay? Yeah?
For each item in each array, just compare
Exactly. So what you do is you start down here at the beginning of each array, each half array, and you compare the first element in the first half with the first element in the second half, and figure which one is smaller. That is, and then we actually, there's a second array you're not seeing here. We'll put this first element over into a second array. Okay? Then we'll compare the first element of the first array with the new first element of the second array, and we're going to find out the one over here is smaller, so it's copied over. So we just make one pass through both arrays in parallel, and comparing two elements, copy the smaller one over, and they'll get zipped together into a sorted order. Now you don't see the zipping happen here because I'm not showing you the second array, but if we finish, they get merged and copied over. So let me show you what I'm doing. Let me show you extra array. We'll make the speed slow. We will permute it, and then we will run it. Now I'm going to stop it after the two top-level recursions complete. So you can see that as it does the merging, it merges into the extra array and then copies back. So you'll see elements starting to appear over there and get merged. All right, the first recursion is returned. And the second, rats. Okay, that didn't stop it on time. Let me try again. Okay, first half is done. Okay, the second half is done. And now what you're going to see is, the second half is a little past a minute. Start to merge the two halves. So it's just comparing the bottom element on both sides and copying the smaller one over. It does that repeatedly. And there they go. And then at that point, the sorted array is in the wrong array, so it has to copy it back over to where it needs to be. And there it is sorted. But what you're seeing, I stopped to highlight what happened, when the first subarray was sorted, when the second subarray was sorted by the recursive calls, and then the merge operation. What are you seeing in all the times where I'm not stopping? Why do you see stuff flying around over here and start to appear over there and then get copied back into there? What's going on then? So watch it and tell me what's happening while we're waiting to get the first. Right? Why are things flashing over here and appearing over there and then getting copied back over there? That thing's about to get copied in. Why are we seeing that? Funnel that and then copy back. Yeah.
This is just a list, but like when it finishes, what it's doing in with that method, doesn't it like go away so it has to store somewhere? And like since you're returning something.
Okay. I mean that's right, but it's not. There's a better explanation of what's going on. Yeah.
Since it's a recursive function, it's doing the same thing that the large array is doing. So it's going to be like taking all of the stuff on one half of the first half, and then half of that half, and then half of that half.
Exactly. There's a whole bunch, it makes two recursive calls. Those two recursive calls make recursive calls and so on. The base case is the array contains one element. One element array is already sorted, nothing to do. You'll notice, if I do this again, that for the first half of the time, nothing will be touched. None of these elements over here are going to move, and nothing will appear over here. So let me start it again. I'll slow it down slightly. Okay, notice that nothing over here is being messed with until now. And so what you were seeing on the left was the recursive calls required, the comparisons in the recursive calls are required to sort the left half. Okay, this is harder to get a grip on by just looking at the animation. But you ought to be able to see that it is a lot faster than insertion sort and selection sort. Right? Let's see what size we are at. We're at 128, and we only did 727 comparisons, whereas we were doing thousands for insertion sort and selection sort. Let's double the size and see what happens. So 727, and let's run it again here. And go. Okay, so it did 1,700 comparisons. So it turns out that merge sort is not linear, okay? But it's not quadratic either. It's something called n log n. So it's proportional to the function n times the log n. Slightly worse than linear. So if you double the size of the array, the number of comparisons goes up by a factor of 2 plus some extra. Okay. So 1734, if we went to up to 512, we should end up with probably about 4,000 comparisons. That's a little more than. Yeah. Okay, so that's characteristic of merge sort. Now, you think merge sort has a worst case. That's markedly different from the average case we're seeing here. In other words, what would happen if we sorted those 256 elements there? Turn this off just to make it a little darker up front. What do you predict? Kind of asking a lot to make that prediction, but yeah?
Will it still do the same number because it has to still cuts it in half? And
Yeah, yes, it turns out that it's completely insensitive to the data. So if we go and sort this, maybe it's not completely insensitive to data, but it's pretty close. So it did 1,024 comparisons. Okay, so I said it's completely insensitive. The merging step itself can be twice as fast if it's sorted versus sorted in the opposite order. So if I permute it, wrong thing, put it in descending order and sort it, I'll get the same thing there. Anyway, my predictions aren't working out either. The thing to remember about merge sort is it's way faster than insertion sort and selection sort. There's no reason to ever use selection sort, and the only reason to use insertion sort is if the array is sorted or close to it, because then it's fast. Otherwise, you stay away from quadratic sorting algorithms. Can you see a liability for merge sort? We're about to look at quick sort, which is faster still. What do you think it is that's slowing down merge sort relative to quick sort? Even though I haven't shown you merge sort yet, quick sort yet. Yeah.
with memory, is like that?
The what?
Memory stores.
It's not so much the memory, but it's a consequence of the memory. So this uses twice as much memory as the other sorting algorithms because there's an extra array. Yeah?
Is it having to do all the comparisons of the different divisions at the end?
All the comparisons the only place comparisons are done in merge sort is when it's merging. So it's not the comparisons so much as the copying, because we're constantly having to copy things back. We merge into another array and then copy the merged array back. So that tends to slow it down. So quick sort, let's see, we did 10, let me permute it to get it. Okay, so we're looking at the size of 256. We get 1733. If we take that same array and use quick sort, that can't be right. Okay, well, I guess it is. It did more comparisons, but it turns out that quicksort is typically about twice as fast as merge sort because it's done in place instead of having to copy things back and forth. Now, it can be really hard to see what's going on with quicksort, so I'll help you out here. So let me turn this extra array off because we don't need it, and make this smaller so you can see it, and permute it. What merge sort does, or what quicksort does, is it just takes what I'm doing is I take the last element in the array and I rearrange the array so that everything on one side is smaller than the element I picked, and everything on the other side is bigger than the element I picked. And now I've split the array hopefully in half, but not necessarily in half, and then I recursively sort the two pieces. In this case, the smallest element in the array is right here, which is going to lead, no, it's up here, which is going to lead to a very bad split. So I want to permute it again until I get a good split. Okay, the smallest, the rightmost element, of the array is right here. So what it's going to do is rearrange the array so that everything that's smaller than this is going to be in this area, and everything that's bigger than this is going to be up in this area. So I'm going to have to turn the speed down slow, and hopefully I'll be able to stop it in time. Okay, so it's rearranging the array, and it's about done. So what it did was it picked the rightmost element and then split the array so that it just rearranged everything so that the right side has small elements, the top has big elements. Then it recursively sorts the two halves and it's done. There's no merging step required. So it partitions the array and then sorts. So what you'll see next is this glob here will sort of be pinched in half. And eventually this will all be sorted and then it will start working up here. So let me start it again. So it's recursively splitting, so now it's finished with the original left half. Now it's at partition again. You can see that choke point up here. You can see it keeps partitioning on smaller and smaller pieces of the array, and eventually everything is sorted. And that's nice. If you look at where the comparisons are happening, let me do this again. I'll permute it, but I'll put the speed up fast and we'll start it. So remember, for insertion sort and selection sort, the array was largely filled with the black comparisons. But here, quick sort, relatively few comparisons. The number of comparisons is much closer to n than it is to n squared. Now, something about quicksort is if you give it something that's already sorted, it's terrible. It's worse than insertion sort. That's fast. So insertion sort, quicksort's bad if the array is already sorted, or if it's in descending order. So we get the similar kind of thing. Well, it is kind of interesting to watch how the effect is to sort the two sides sort of grow like that. Okay, so I've shown you two quadratic algorithms, average case, and two n log n algorithms in the average case. N log n is pretty close to just n, pretty close to just linear. Now, just for the heck of it, I'm going to show you a couple more. I'm not going to try to explain anything about their complexity or how they work. Something is slowed down on here, so I'll restart it. Let's go to 256 elements. I'll permute them. I'll put the speed to moderate. So here is one called shell sort. It's based on insertion sort. What it does is it makes a number of passes and it keeps getting closer and closer to sorted. It roughly sorts it and then sorts it more finely and then more finely and then finally the last pass is going to put it all together. So that's shell sort. This one is called heap sort, and I have no chance of explaining why it works, but I want you to know something strange about it. See anything odd? There's two passes. In the first pass, it almost sorted in reverse. It wasn't completely sorted, but it sort of tried to put it into reverse order before it started putting things in the correct order. I'll run it again so you can see it. So it's sort of moving things so that it's sort of in a band from left to right, upper left to lower right. If we sort something that's already sorted with heap sort, it does something weird. You put it in that order and sort it with heap sort, get that effect. And finally, here's something called radix sort. Now, I think I know what's happening here. I need the extra array because it doesn't copy. So it uses an extra array. Let's preview it and slow it down. So it's going back and forth from one side to the other, gradually putting it into sorted order. Radix sort is linear time sort, but it cheats by not doing comparisons. It's a special purpose algorithm. You can use it to sort integers. It basically takes integers apart into their bits and bytes and uses that to sort. But typically we're interested in comparisons-based sorting algorithms, like the other ones I showed you. And for those, the fastest you can get is n log n in the average and worst case. Okay. Let's stop there with sorting. Let's take a break, and then we're going to look at something different. Okay, so let's consider another simple algorithm, or this is much simpler than sorting. It's just a linear search. So the idea is we have a sorted array, and we want to find out if 45 is in the list. So what we're going to do, just imagine running a loop that compares 45 to 1, and then 45 to 3, and then 45 to 7, and keeps going. Okay? And let's just count how many steps it takes. And again, we'll count steps in terms of comparisons. So we compare, let me go back, we compare it to the 1, it's not the same. 3 is not the same. 7, all these comparisons fail. When can we stop and say it's not in the list? Okay, when we get to there, we see 45 is not equal to 50, and furthermore, 50 is, since the array is sorted, 50 is bigger than 45. 45 can't possibly occur in the rest of the list. So that's a linear search. It took 12 probes, 12 comparisons to decide that the element's not in the list. Now, is this a good algorithm or a bad algorithm for solving this problem? Okay, turns out it's bad. Now, this is bad because it takes linear time. The amount of time it takes is proportional to the length of the array. So in the case of sorting, linear time is great. In searching a sorted array, it's terrible. How many probes on average would it take to decide that a randomly chosen element is not in the array? If they're n elements at all. Yeah?
N over 2?
N over 2. The idea is sometimes the element you're searching for will be, we're going to have that element chosen randomly. It'll be small, and we'll find out right away it's not on the list. Or it might be large, and we'll have to look at the whole list to find out it's not there. On average, you'll look through about half the elements. Not so bad when the array is that long. But if the array is 1 million elements long, that's 500,000 comparisons. It's going to be expensive. So there's an algorithm called binary search that can do this much faster. As a preface to that, I'll tell you, when I was a kid and I would go to church and I'd get bored, one thing I would amuse myself with was to take the hymnal, which had numbered songs, about 500 of them, and see how fast I could turn to the right page for it. So if it's like hymn number 431, you sort of guess where to go to, and if you're looking at hymn number 350, you knew that the hymn had to be in the back half, otherwise in the front half. So I would always challenge myself to do it with 5 probes or less, and I got pretty good at it. That's similar to binary search. So with binary search, what you do is, if you're trying to find out if 45 is in the list, you don't look at the last element, you don't look at the first element. What do you do? Open that hymnal in the middle and see what hymn is there. Well, it's hymn number 24. So we know that that's not 45. What else do we know?
That it's great.
Right, it's not going to appear to the left of the 24. If it's in there at all, it's going to be to the right of 24. So with one probe, you rule out half of the elements in the array. In the previous case, we had to look at every single one of those elements before we ruled out them all. So you get a lot of bang for that first comparison. Okay? So we've got now 1, 2, 3, 4, 5, 6, 7 elements left. Where should we look next? Right, look at the middle element of what's left, which is at 50. Now the 50 is bigger than the 45, so what can we rule out?
The right side.
Rule out all those. Then we can probe the 33, which is the middle of the remaining elements, and it's too small, and there's only one left, and it's not 45. So we're done. That took 4 probes. Okay, 4 probes versus 12 probes. That's not a big deal, but here's the. We decided the linear search took n over 2 probes on average. It turns out that for binary search, it takes log base 2 of n probes to find out an element's not in the array. Now, what is the log base 2 of a number? Yeah.
It's 2 to the nth, right?
Well, no, it's the inverse of 2 to the n. There are lots of ways to think about log base 2, And I'm sure if you take 2420, you'll get familiar with them. But I'll give you this definition. It's the log base 2 of a number is the number of times you can cut it in half before you're only left with 1. So what would be the log base 2 of 8? 3. You divide 8 by 2 once to get 4, and then again to get 2, and then again to get 1. So it's 3. Log base 2 of 32 is 5. Log base 2 of 64 is 6. Log base 2 of 40 is somewhere between 5 and 6. Okay? So why does it make sense that it takes log base 2 probes? Log base 2 of n probes here, yeah?
Maybe you're like cutting the array in half and like checking if it's on which side of the array, then cut that side in half.
Exactly. We're cutting n in half until there's only one element left. Okay? So if you might want to fall back on that definition sometime in the future. If you're confused by other definitions, just keep in mind what I said. It measures how many times you can cut something in half before there's only one thing left, or one piece left. Is that a big difference, n over 2 compared to log base 2 of n? Okay? It's a massive difference if the number's big enough. So right here, I said 1,000,000 elements before. If you have a 1,000,000 element array, divide that by 2, you get 500,000 probes to decide on average that something's not in the array. On the other hand, log base 2 of 1,000,000 is about 20. So it would only take 20 probes to decide something's not in the array if you did a binary search. Huge difference. If you go to 1,000,000,000, 1,000,000,000 divided by 2 is 500 million. Log base 2 of 1,000,000,000 is only 30. So that's why you do binary search when you can. All right, now we're going to talk about linked lists. You probably spend a month and a half getting to this point, and I'm not sure when you get to it, 2420, but we're taking an accelerated pace. Yeah.
I just wanted to ask you, so the binary search works if it's sorted. If it's unsorted, you just have to do it.
Okay, so binary search requires the thing to be sorted. If it's not, you can always sort it and then search it with binary search. Is that a good idea or a bad idea? Like most other things, it depends. What does it depend on? Yeah.
How many times are actually searching through
Yeah.
certain elements?
How many times you're going to search it? If you're just going to search it once, it's not worth sorting it first. You just do your linear search. That's faster than any sorting algorithm. And get your answer. On the other hand, if you're going to sort it a bunch of times, search it a bunch of times, it makes sense to sort it first and then do a bunch of binary searches. Okay. You know that in Java there are array lists and linked lists, and I've never said much about the difference. I did show you, I gave you an idea of how array lists are implemented, and they're implemented using arrays that are sometimes have to be doubled in size and copied over. But let's look at linked lists. They're a little bit different. So what I've got up there at the top is a picture, a way to visualize a linked list. And the way to think about a linked list is, a linked list is a collection of these objects. So each one of these boxes is an object. Each object contains two things. A value, so this is a linked list of integers, so it contains a 1 there. And then what comes next is a reference to the next object in the chain. So it's just a bunch of chained objects. And they don't have to be next to each other in memory. So this thing here might be in one place in memory, and this might be millions of bytes away in memory. It doesn't matter. You just have the memory address, or the way it works in Java is you have a reference to the next object, a reference to the next object, a reference to the next object, and then what's that slash? That's a null reference to tell you that's the end of the thing. And if you wanted to make a class, these are some, you would need 2 instance variables. So anytime you create an object of type link, it's going to be one of those boxes, one of those 4 boxes. So there'll be a value field, which is the actual value that's stored in the list, one of the values that's stored in the list, and then that link to the next, the reference to the next link. And the constructor, when you create a link, it's going to want to have a int as a parameter and a link as a parameter, and it just records them. And then we'll have other methods, like ways to extract the value and the next, and ways to set them. That's pretty simple. So that's what a linked list is. Now, looking at that linked list and comparing it to an array in your mind, what do you think? Why would you ever want to use a linked list? It seems more complicated. Yeah?
You want to use it when you want to save time on the array list. Whenever you insert something, it has to shift everything to keep it sorted.
Okay.
This one, all it does is have to change the reference
Okay.
points.
So linked lists work well when you need to change them. If you need to insert between the 7 and the 4, for example. You don't have to do any copying. You just splice in a new element. And I'll show you how that's done. On the other hand, linked lists are terrible sometimes as well. When are they terrible compared to arrays? What would it take to get the, suppose that's the list and I ask you to give me the element at index 3. So that 8 is at index 3, yeah.
You have to start at index 0 and keep going to 3.
Right, we'd have to start at the beginning of the list and walk the list until we get to the end. And that's okay when there's 4 elements on the list, but imagine a 1,000,000 element list. To get the last element, you got to walk the list very slow. Whereas with an array, you just go right to that element. So you use linked list when you plan to do a bunch of insertions in the middle. Otherwise, use array lists because they got fast random access. Okay, so let me show you how to build this list. So I'll go back here. I showed you that constructor right there. It takes in the int, the value stored in the link and the link to the next element, the reference to the next link. So what do? Is we first create a linked list whose value is 8 and whose next field is null. And then we got that picture right there. All right? Then you do this. You say, okay, now create a new link that contains a 4 and has a reference to the original list. And you got that. So you just build it backwards. You get the 8, the 4, the 7, and the 1. In the end, you have a reference to the link containing 1, which contains a reference to the link containing 7, and so on. So that's how you would build that picture. Now, let's look at how insertion is done. We want to insert a 5 between the 7 and the 4. All right? Let's see what the steps are. First thing we're going to do is create a new link. We're going to we want to insert between the 7 and the 4, so we got to get to the 7 first. So I do list.getNext, and that gives me that reference before, which points to that 7 box. All right, what do we need to do next? How are we going to get a box? We want a new box where 7 refers to that new box, and that box refers to the 4 box. So somehow we've got to squeeze something new in here.
The 5 just go there, and then the 7 will point to the 5, and the 5 will point to the 4.
Yeah, so it's going to take 2 statements to do that. So let's see what's first. I create, I just call the constructor. I say, all right, give me a new link object that contains 5. That's the element I'm trying to insert. And refers to before.next. I think I should have called it getNext. I have a typo there. So you end up with that box with a 5 in it. It's not part of the linked list yet, but at least 5 is in the right spot, and that reference to the 4 box is the same. What's the next thing we need to do? Yeah?
You have to connect 7 to 5.
Okay, we need to connect 7 to 5. How do we do that? Yeah?
Could you do before equals new link?
Well, changing before won't do anything. We need to change that 7 box. What do we need to do to the 7 box? Specifically, what do we need to put right here? Yeah?
Set its next.
Say it again.
Set the next value to the new link you just created.
Right. We make it so that what's contained in here is this new link reference. So it looks like that. We say before.setNext. So we set the next the next field of the before object to be new link, which is this. So now in 3 statements we've done that insertion. And it doesn't matter how long the list is, the insertion works the same way. That's assuming that that you don't spend all your time getting to the point where you need to do the insertion. If you're already where you need to go, you can splice something in cheaply. Yeah.
So just to kind of like understand this, so with a linked list, it's going to take like 3 statements in your code to like, in your own code to like put it in, compared to an array list which has to go through every element in order to.
Yeah. To insert into an array list, you're going to have to copy, say you want to insert in the middle of an array list, you're going to have to shove everything over by one element to make room to stick something in there. So inserting in the middle of an array list can be expensive. Inserting to the end isn't so bad, but into the middle is a trouble. Yeah.
Is there any purpose in making a function like lists where you have 17 things off the side linked into 4? Or would that never be done?
Well, to be a linked list, it's just going to be a single chain. But more generally, what you study in 2420 are linked structures. So you end up with trees, binary trees, where each box will contain 2 links to a left child and a right child. But what I'm trying to show you here is why it's inexpensive to insert into the middle of a linked list. Yeah?
So, in this case, though, would you still have to start out at the beginning and then travel all the way to the 7?
Okay, so he's saying, suppose it's 1 million elements and you want to insert into the middle. You're exactly right. You're going to have to pay a huge price to get to where you want to do the insertion. So this is only good if, let's say you're in the middle of traversing a list to look at all the elements as you go, and you decide, I want to stick an element here. Assuming you've already paid the cost to get where you're going, insertion is cheap. But no, getting to the insertion point can be expensive. Or trade-offs. Okay? Now, what would code look like that printed out all the elements in a linked list? So it takes as this parameter, let's say it starts with list right here. Yeah?
You said the loop that if the reference to the name isn't null, then print that like that.
Okay. So let's see what we're doing here. We're just creating a local variable link to hold the value of list. So link now refers to this thing here. And then while link is not equal to null, we print out link.getValue. So that'll print out the 1, because initially link refers to this object. We print out the 1. And then we say link gets link.getNext. So then what will link refer to? To this one here. So then it will print out the 7 and move link to point here. That'll print out the 5 and change link to point there. That will print out the 4 and change link to print here. That will print out 8 and change link to what? Null. And that'll stop the loop. So that's typical of the code it takes to walk down a linked list. And the idea is, as you do that, if you're looking for a spot to do an insertion, when you get to the spot, it's cheap to do the insertion. Yeah?
Is there a type of data structure that contains both the reference to the next element but also an index? Or would that be kind of pointless?
So he's proposing merging the ideas of an indexed array, constant access being an index, to the linked nature of a linked list. I don't know if there's a name for such a thing. You can imagine it, but the problem would be if you had, imagine you had an array with references into the linked list, so you could do immediate indexing. When you do an insertion into the linked list, you're going to have to do an insertion into the array, and that's going to take. You're going to have to do a lot of copying there. There's no perfect data structure that does everything perfectly here. Let's look at some of this in code. So here I have an array list that's implemented and a linked list. So this is a linked list class. So I called it my linked list, and let's see what it contains. It contains the size of the list, and it contains a link. And a link is just what we've been looking at. So a linked list object is going to contain the number of elements in it, and a reference to the first element in the chain. So the job of this class is to maintain the chain. So what would an empty linked list look like? We've got to set those instance variables. What should I set size to? Yeah, initially there are no elements. And remember, root is one of those chains of link objects that we just looked at. We're just putting it inside the linked list object. So we've got the linked list object, which contains these two instance variables. This is then a reference to a chain. So what do we need to set root to in the case where it's empty? Null. The chain is empty. There's nothing in the chain, so we'll start at it null. Okay? So there's our constructor. I've already got these implemented. So the get, you basically, to get something in a specified index, what that method does is it walks down the chain, index times, and then gives you the value out. Set does the same sort of thing. Append. What's it take? Suppose we have a linked list and we want to append to the beginning of the list. We need a picture to talk about that. So suppose we have this chain here. What's it going to take to, we'll call this root. What's it going to take to put a new number, let's say 6, at the beginning of that chain? And let root be the value of that new chain, the reference to the new chain. This is a special case of inserting into the middle. If we want to create a new chain, we've got to create a new box. So we'll create a new link. We'll store 6 there. What should we store right here? We need to store basically this arrow there. So whatever the value of root is becomes the new value of this box. So we just copy that arrow there, and then what should the new value of root be? It should be the reference to that box. Okay? So in terms of code, what we're going to say is root equals new link. Okay? And we want to put, link takes 2 parameters, the value that's stored, that's val, and the reference to the next thing. Well, what is the next thing? What's that? So we already had a chain. Not even root.getNext, just root. Okay? Root already referred to the first element in the list. So what we do is we create a new link that contains val and root, and then the reference to that link becomes the new value of root. So we've just extended it to the left. We've added to the beginning of the list. So that's typical of manipulations you end up with linked lists. What does it take to add to the end of the list? Oh, we forgot something. We've also got to add, the size just went up by 1, so we need to do that. What's it take to add to the end? Let's do the case where the root is null currently, so the list is empty. Yeah?
If root is null, then you just gotta make root something.
Okay, so you say root equals new link, and what goes, so it contains that val, and what does it reference? Yeah, null. It's a list of length 1. So that's good. What do we do otherwise? Oh, we need to remember to do. What if it's not null? So let's say we got this one here. We want to insert something at the end, like an 8. How are we going to do that? Yeah?
Are we gonna have to march through the whole thing?
We need to march through the list until we get to the last element. And then what do we do when we find the last element?
That's pretty much the same thing that we added.
Basically, that didn't work like I wanted.
That
We create this thing right here and then store a reference to it to the last element in the list. Okay? So we have a way of marching to the last element. It's called getLink. You just tell it the index. So we'll call getLink. Oh. What will be the element of the last thing in the list? Let's say there are n elements in the list. What would be the index of the last one? Yeah.
I think it would be the index out of size.
Well, it'd be size minus 1 because it's 0 based. So that returns the last link. And then we just got to call set next on that link, and we'll give it a new link that contains val and null because it's at the end now, and then we increment size. So those are a couple simple implementations to do surgery on linked lists. We can add at the end, we can add at the beginning. So let's do something with this list now. I have an interface called myList, and notice myList has a get, a set, an add first, an add last, and a size. I have a myArrayList that has those 4 elements. So it has get, set, and so on, and we just did that for linked lists. So both these lists implement that interface. So they have that in common. So first of all, I've got a testing class that tests this will run a bunch of tests against array lists, my array lists. So I'll run those, and they all pass. And I can instead test linked lists by doing that. And this all works because of interfaces. All these methods are working on my lists. So you can use either a linked list or an array list. Let's see if I've made any mistakes. I did. Let's see what tests. Null pointer exception. What the heck? Didn't expect this to happen. So it's right here. If root is null, we're setting root that way. And let's set a breakpoint there and try debugging this one. Okay, let's step into that didn't work. All right, let's review our code here. Help me out here. So a linked list has a size of 0 and null is the root. Does that make sense? Okay, we've got get link here. Oh, I didn't implement get link. Okay, this returns null. How do we get, what do I need to do to make this work? So node starts out being null. We want to move through the list to find the element at the given index. Okay? Yeah.
You do a loop where you keep calling like the get next or whatever.
Mm-hmm. Okay.
So you set node to the root one, and then you call get next on that, and set it to node, and then.
Okay. So what we'll do is we'll let node start out at the value of root, and then I'm just going to do while index is greater than 0. I'm going to say node equals node dot get next. So if index is 0, we first node equals root. So if index is equal to 0, we'll just be returning the root. If index is bigger than 0, we're going to go from node to its next element and subtract 1 from index. If index is still greater than 0, we're going to go one more hop. When index finally hits 0, we'll be at the right spot, and we can just return the node as the answer. So it's like right here. What if we want to know what's at index 2? Well, this is our first node. Node begins life referring to the same thing as the root. Index is greater than 0, so what do we do? I don't know what I did there. It says node gets node dot get next. So what will node point to next? Yeah?
You just go down to the next element in the chain.
Right, so that goes away, and we adjust it so it points here, and this gets changed to 1. What happens now? Index is still greater than 0, so we just move it to refer to the next thing in the chain. Now it's 0, so we return a reference to that one right there. So that's how that method works. All right, back to this. I think we got that working now. Let's run the test again and see. Let's hit the breakpoint again. Never mind that. Okay, so we got the thing working now. Okay, last thing I want to do is do some timing experiments. So I've got a list timer here. It's going to look at things of size 50,000. So what it's going to do is do this timing experiment. So what it does is it's going to call add first 50,000 times and figure how long that takes. And then it's going to repeat the experiment, a similar experiment, and do get 50,000 times and compute an average amount of time it takes. So add last ought to be fast for linked lists, and the get operation ought to be fast for array lists. Let's see if that bears out. So here we go. Still running. Okay. Okay, it does this twice. That's going to take a while, so let's look what's going on up here. Now it finished. Okay, we created an array list, and the add first took on average 9 microseconds each. But the gets on the array list were a lot faster, 0.007 microseconds. Linked list, on the other hand, was quite a bit faster for the add firsts, but disastrously slow for the gets. So that just shows you it's a real thing. Random access, which is the gets, is much better for an array list than for a linked list. And on the other hand, inserting near the beginning of the list is bad for array lists and fast for linked lists. That was averaging over 500,000 elements. We double the number of elements, and we still see the same thing. So this did what you'd expect. The time it takes to do the add first for the array list increased. In this case, it doubled. And the gets are still fast, and it's just the reverse of the linked lists. So this is, admittedly, this is a fast taste of algorithm analysis and sort of a preview of things that are in store for you if you take 2420. A lot of students find it very eye-opening to take 2420 because in addition to programming, you've learned you've learned a little bit more about Java, but mostly you've learned what there is to know about Java. And instead of just using Java to write programs, you'll be using Java to implement data structures and algorithms like I've done here, and starting doing real science on them, real analytical measurements and analysis and comparisons, drawing conclusions and writing up your results. So it's sort of like computer science with a physics lab on the side in a way. Okay, any last questions before we wrap up? Okay, I'll see you for a review on Wednesday.